Günaydın arkadaşlar. Umarım iyisinizdir. Beni duyabiliyor musunuz? Sesle görüntüde bir problemimiz var mı?
Bir sorun yok hocam.
Teşekkür ediyorum. Geçtiğimiz hafta ders hakkında biraz konuşmuştuk. Bu hafta doğrudan artık bir girişle başlayacağız. Ama başlamadan önce sorusu olan var mı? Geçen hafta katılmayanlar için öncelikle şeyi tekrar edeyim. Slaytları sizinle paylaşmıyorum. Çünkü slaytlar zaten kitabın sitesinde var. Linkini geçen hafta paylaşmıştım. ostreebook.com olması lazım. Bakarsınız. Bütün slaytlar ve yardımcı materyaller orada var zaten. O yüzden tekrar sizinle paylaşmayacağım. Onun dışında sorusu olan yoksa doğrudan başlayabiliriz. Var mı soru? Okay then. Let's start with an introduction to our operating systems course. In this chapter, we are going to cover these subjects. We are going to discuss what operating systems do. We are going to discuss computer system organization. Actually, these chapters will going to covered by us briefly. We are not going to deep dive organization or architecture because our main focus will be on operating systems. But these are some important points before discuss the main topics of operating systems. So we are going to cover operating system operations, resource management, security and protection, virtualization, distributed systems, kernel data structures, computing environments, and maybe we can discuss the free, libre, and open source operating systems. And these are our objectives for this chapter. We are going to describe the general organization of a computer system and the role of interrupts. We are going to describe the components in a modern multiprocessor computer system. We are going to illustrate the transition from user mode to kernel mode. We are going to discuss how operating systems are used in various computing systems, and we are going to provide some examples of free and open source operating systems. Basically, an operating system is a software that manages a computer's hardware. So it also provides a basis for application programs and acts as an intermediary between the computer user and the computer hardware. As you know, operating systems are everywhere, from cars and smart home applications that include the Internet of Things devices to smartphones, personal computers, enterprise computers, and cloud computing environments. So we are using operating systems in every aspects of our lives. We have just described the operating system as an interaction environment between users and computer hardware. From this perspective, we can talk about three goals of an operating system. The first one is execute user programs and make solving user problems easier. And the second one, make the computer system convenient to use. And the last one, use the computer hardware in an efficient manner. So these three goals can be described as operating system goals in this perspective. Now we can start to create an answer to the question that what operating systems do by looking at the operating system's role in the overall computer systems. As you know, a computer system can be divided roughly into four components: the hardware, the operating system, the application programs, and a user. The hardware, actually, we are indicating the central processing unit, the memory, and the input-output devices as describing the hardware. The hardware provides the basic computing resources for our computer system. The second part is operating system. The operating system controls the hardware and coordinates its use among the various application programs for the various users. The application programs such as word processors, spreadsheets, compilers, web browsers, games, defines the way in which these resources are used to solve users' computing problems. And the last part is user. Also, as you can see from here, users could be people's, machines, or other computers. Here you can see an abstract of components of a computer from hardware to user. At the base level, we have computer hardware such as CPU, memory, I/O devices, etc. And we have an intermediate level between computer hardware and application programs. So actually, we can describe an operating system in this manner. We have an intermediate layer which users or application programs can use the computer resources. So we need operating systems to create an interface between hardware and the user or application programs. To understand the operating system's role, we can explore operating systems from two viewpoints, that of the user view and that of the system view. So the operating system's responsibilities depends on the point of view. For example, users want ease of use and good performance, and they don't care about resource utilization. For example, if you want to play a game on your computer, you don't care the resource allocation in the background, you just need performance. But on the other hand, shared computers such as mainframes or mini computers must keep all users happy. They have more than one users and they have to provide performance to all their users. So from this point of view, operating system is a resource allocator and control program making efficient use of hardware and managing execution of user programs. So based on the design, different hardwares needs different type of resource management, such as workstations, servers, mobile devices, or even embedded computers in autonomous vehicles needs operating systems based on these needs, because all of that structures need resource management. So based on the hardware, that devices need different resource management techniques. As you can see that the term operating system covers many roles and functions. Because of the lots of different design and uses of operating system, we need different roles and functions to define what operating systems do. Because we have computers in cars, ships, televisions, and all of them has different functionalities and different hardwares, we need to cover all the functionalities and goals or roles in these definitions. So actually, to understand the operating system concept, we can take a look at the history of computers. Basically, the operating systems are born when fixed use computers for military purpose became more general purpose and needed resource management and program control. At first, the computers used for fixed jobs, so we don't need to manage resources because they have just one job. But when we started to use that computers for general purposes, that means we need different tasks and we need more than one user, so we have to create a management system for that resources. So resource management and program control means we need an operating system there to handle that needs, because resource management and program control is not part of the hardware. Also, they're not parts of application programs. We have to provide that interface for users or to use our hardware. So for that reason, at the beginning of the operating system's history, resource management and program control means we need to create an operating system to handle that needs. So we can basically say that we don't have a universal accepted definition for operating systems. Then that's the question, how we can define what an operating system is. Actually, as I said, we don't have an universally accepted definition, but still we can try to make a definition. For example, everything a vendor ships when you order an operating system is a good approximation, but varies widely. So basically that means, okay, you buy a Windows operating system and Microsoft provides you tons of programs. You can describe that package as an operating system. Or let's assume that you installed a Linux distribution to your computer. So when you install that distribution, some programs installed to your computer, you can define that package as a whole as an operating system. But as you can guess, different operating systems provide different functionalities when you make a fresh install. So, okay, we can use that definition, but it's not a very well definition. A more common definition, and the one that we usually follow, is that the operating system is the one program running at all times on the computer, usually called the kernel. So basically, when we call operating systems, generally we are pointing the kernel, which is a program running at all times on the computer. Along with the kernel, there are other types of programs, system programs which are associated with the operating system but are not necessarily part of the kernel, and application programs, which include all programs not associated with the operation on the system. So basically, we have a kernel, and apart from the kernel, we have system programs and application programs. System programs ships with operating system, but they're not part of the kernel. Also, we have application programs which are not associated with our operating systems. But today, we need another definition, because mobile operating systems often includes not only a core or kernel, but also include middleware, which is a set of software frameworks that provide additional services to application developers. So in many mobile operating systems, that middleware is a part of the operating system. So in that manner, we can change our definition. In summary, for our purposes, the operating system includes the always running kernel, middleware frameworks that help application development and provide features, and system programs that help in managing the system while it's running. So we can make a summary for operating system like that. The operating system includes the always running kernel, middleware or frameworks that help application development, and system programs that help managing the system while it's running. Now we are going to continue with the overview of computer system structure. I have a general scheme here. As you know, a modern general-purpose computer system consists of one or more CPUs and a number of device controllers connected through a common bus that provides access between components and shared memory. This concurrent execution of CPUs and devices competing for memory cycles, because as you can see, we have CPU, we have different device controllers. In this example, we have this controller, USB controller, graphics adapter, and they're connected via the system bus, and they're all using the same shared memory. So that means if they are using the same memory, and if you want to execute that operations concurrently, we need to manage that resource. In this case, memory is a resource, so we have to provide an interface for managing that memory in the perspective of the operating system. Now, I'm going to continue with this scheme. Each device controller is in charge of a specific type of device. For example, in this example, we have this drive, audio device, or graphics display. A device controller maintains some local buffer storage and a set of special purpose registers. The device controller is responsible for moving the data between the devices, and then it controls and its local buffer storage. So that's the purpose. The device controller is responsible for moving the data between the devices that it controls and its local buffer storage. Typically, operating systems have a device driver for each device controller. If you have a good, well-functional operating system, that means it's going to provide a device driver for each your controller. This device driver understands the device controller and provides the rest of the operating system with a uniform interface for devices. Okay, so you have different devices, you have different device controllers. So based on that, you need device drivers for every controller. So using that device driver, your operating system can communicate with different drivers in the same manner. The CPU and the device controllers can execute in parallel, competing for memory cycles. So that means we said that the job of the purpose of device controller is to move data between its local buffer and memory. And also we know that central processing unit needs memory space while making its operations. So that means the CPU and the device controllers can execute in parallel. So they can be compete for memory cycles. To ensure orderly access to the shared memory, a memory controller synchronize access to the memory. So device controller informs CPU that it has finished its operation by causing an interrupt. So we have an important term here, interrupt. Hardware may trigger an interrupt at any time by sending a signal to the CPU, usually by way of the system bus. Because we have a connected system bus, we have connected devices, so that hardware devices use that system bus to send an interrupt or trigger an interrupt to CPU. Also, interrupts are used for many other purposes, and they are a key part of how operating systems and hardware interact. Interrupts are an important part of a computer architecture. Each computer design has its own interrupt mechanism, but several functions are common. The interrupts must transfer control to the appropriate interrupt service routine. Interrupts transfer control to the interrupt service routine generally through the interrupt vector. We have an interrupt vector, and using that interrupt vector, interrupts transfers the control to that service routine, which contains the address of all the service routines, and interrupt architecture must save the address of the interrupted instructions. You have an interrupt vector. That interrupt vector provides the addresses of service routines. So based on your interrupt, you can look up that vector and you can find the right address for your service routine. Also, we have some new terms, trap and exception. A trap or exception is basically a software-generated interrupt caused by either by an error or a user request. Basically, when we say interrupt, we generally indicate that that call comes from an hardware, but also softwares can generate interrupts too, and generally they called as trap or exception. So basically, we can say that an operating system is interrupt driven. So this is one of the important parts of our course. We are going to discuss the operating system concepts, but at the base level, we can directly say that an operating system is an interrupt-driven system. So that means we have to handle that interrupts. Okay, when an hardware needs a special attention based on the CPU cycle, it creates an interrupt. Also, softwares or users can create traps and exceptions too. So the job of our operating system is to handle that interrupts. We have to give answers to that calls to create a functional operating system. So here's the question: how we can handle the interrupts? The operating system preserves the state of the CPU by storing the registers and the program counter. Then determines which type of the interrupt has occurred, and separate segments of code determine what action should be taken for each type of interrupt. So basically, this is how we can handle the interrupt. In this case, we are assuming that the CPU is executing some operations, and when an interrupt arises, we have to answer that interrupt. So for that reason, we are preserving the current state of our CPU and then determining which type of interrupt has occurred. So based on the type of interrupt, we can execute that service routine. After that, we can again return the previous job of our CPU. Here you can see the I/O cycle. Actually, this is an interrupt drive I/O cycle. At the first step, device driver initiates an I/O. So let's assume that a user, let's say, press a button on your keyboard. So that means the device drivers for your keyboard is going to initiate an I/O operation. So I/O controller initiates then I/O. Then when the input is ready or output is complete or an error is generated, CPU receives an interrupt and transfers control to the interrupt handler, because when an interrupt arises, we have to handle that. So for that reason, when CPU receives the interrupt, it has to transfer its program control to interrupt handler. Interrupt handler processes data and returns from the interrupt. After that point, CPU resumes processing of interrupted task, and this is called as I/O cycle. When a new I/O is initiated, this cycle will be initiated again and again for every interrupt or every I/O. In this case, we are just describing an interrupt-driven I/O cycle. We have basically two methods for handling inputs and outputs. The first one, after I/O starts, control returns to user program only upon I/O completion. On the second one, after I/O starts, control returns to the user program without waiting for I/O completion. So that means we have two methods. In the first one, we have to wait for the getting done of that job before returning to control. And the second one, we can start the I/O and return the control immediately without waiting for the completion of that job, that process. So these are two different I/O structures or two different methods for handling I/O. Okay, we are going to continue to computer system organization with storage structure. The CPU can load instructions only from memory. So any programs must first be loaded into memory to run. So if you want to execute a program, if you want to run a program, that means, first of all, you have to load that program to memory. General purpose computers run most of their programs from rewritable memory, as you know, called main memory. Also, we can call that as random access memory or RAM. Main memory commonly is implemented in a semiconductor technology called dynamic random access memory. Ideally, we want the programs and data to reside in main memory permanently because, okay, we need programs and we need some data to execute that programs. In an ideal world, we want that data and codes stored permanently in our main memory. This arrangement usually is not possible on most systems for two main reasons. The first one, main memory is usually too small to store all needed programs and data permanently. Okay, in today's world, we have more complex computer systems. We have more main memory in the manner of size, but still the main memory capacity is not enough to store all needed programs and all data permanently on our devices. And the second one, main memory, as we mentioned, is volatile. That means it loses its contents when power is turned off or otherwise lost. So, okay, you can, if you have enough storage on your main memory, you can store lots of information, but still it's volatile. When you lost the power or when you turn off your computer, that data will be lost. For that reason, most computer systems provides secondary storage as an extension of main memory. The main requirement for secondary storage is that be able to hold large quantities of data permanently. For that reason, we generally store our data, let's say multimedia and different types of large data, or our programs, program codes on secondary storage. As you know, the most common secondary storage devices are hard disk drivers. And also, nowadays, we are using non-volatile memory devices, or we can call them as SSDs, which provide storage for both programs and data. We can store our programs and we can store our data on hard disks or SSDs. Most programs, they could be system programs or application programs. It's not important at that point. Most programs are stored in the secondary storage until they are loaded into memory. So we store our programs on secondary storage. When we want to execute that program, it could be a system program or an application program. It does not matter in that point. When we want to execute, when we want to run that program, we have to load that program from secondary storage to main memory, and then we can execute that program. So as you can guess, we need a management operation here too. We have our operating systems has to manage the relationship between secondary storage and main memory. We're going to connect this point to operating system. Okay. The wide variety of storage systems can be organized in a hierarchy according to the storage capacity and access time. As a general rule, there is a trade-off between size and speed, with smaller and faster memory closer to CPU. So we know that registers we used on CPUs are faster, and the secondary storage, let's say HDDs, are slower in that manner. So we have a trade-off between size and speed. We have lots of capacity on our secondary storage, but it could be slow. We have small amount of registers in our CPUs, but we know that they're very fast in the manner of using the memory. So as shown in this figure, in addition to differing in speed and capacity, the various storage systems are the various storage systems can be categorized as being volatile or non-volatile. Volatile storage, as we mentioned before, loses its contents when the power to the device is removed. So data must be written to non-volatile storage for safekeeping. We have to store that data in non-volatile storage if we want to access that data again and again. So as you can see, these size actually indicates that the capacity. We know that actually nowadays in our general purpose computers, we don't use general optical disk or magnetic types. For that reason, they are generally called as tertiary storage because they are not directly part of our computer systems. We can use them to safekeep important data apart from our computer system. In the secondary storage level, we have hard disk drives and non-volatile memory, or let's say SSDs. We have hard disk drives and SSDs. These are the secondary storage, and they are in the they have larger capacity than the main memory or cache. Also, they are non-volatile. For that reason, we are using them as secondary storage, but they're a bit slower than the main memory or cache. At the top, we have main memory, cache, and registers. They are called as primary storage or main memory. Generally, we call all of them as main memory or primary storage. They're very fast. We can access, actually, the central processing unit access that memory easily and fastly, but they have a smaller storage capacity. Also, they provide volatile storage. That means when we lost the power, when we lost the electricity, the data on the primary storage will be lost. For that reason, if you have important data and if you want to store your data or programs as in non-volatile manner, you have to use secondary storage. So for that reason, we need a secondary step to manage our memory. Okay, we are going to continue with how a modern computer system works, but before that, let's take a break. I'll be here in 10 minutes.